May the force be with us. I'm not a Star Wars fan, but I thought I'd throw it in there. Since we're dealing with forces,
Yeah.
and you guys Star Wars fans,
Yeah.
you are
Huge.
huge.
Yeah.
I'm sorry. Give me Spaceballs, and that's fine. Are you a Spaceballs fan?
No.
Oh, why? Because it mocks the Star Wars.
I don't know how you can't like both. I've only watched like half of it, so.
See, I like Spaceballs because it mocks Star Wars. But you know what? If you enjoy it, that's fine. It's good for you. I'm happy for you. We have Newton's first law that deals with inertia. We have Newton's second law deals with force. Net force is equal to mass times acceleration. Forces are vectors. Victor? So you're dealing with vectors. When we're dealing with this net force, this is the sum of all the forces, which means you may have to do vector resolution. Sometimes. And when you have things at angles, just like when we had trajectory two-dimensional motion, your horizontal component was your force or your magnitude, your velocity times the cosine, and the vertical was times the sine. And that's the same thing that's going to occur here. Your force horizontal is going to be your magnitude times the cosine of theta. And the vertical will be f sine of theta, your magnitude, your force times the sine of theta. Because what we're going to have to do is let's think through the dominoes here. Acceleration is a linear motion. Acceleration of an object is linear. Easy for me to say. It's either going horizontal or it's going vertical. Force is dependent on acceleration. Force is dependent on acceleration. So we need to be able to break down forces into horizontal and vertical components also. If we need to. And we will, because eventually we're going to throw friction in here, and then we have to worry about friction. We're on a frictionless table, so we do not have to worry about it right now. It's our top view. We have... That was close. I'm still pretty amazed at being able to push, and it actually goes, it veered or whatever, and hit that thing square. Still amazed by that. Little things amuse me. Those are the little things in life. When you're 57 and you're old, you find the little things in life that amuse you a little bit more. That's one of them. We have a top view, flexing on a frictionless table. We have 8 newtons going this way, 6 newtons going this way, 2 newtons going this way. If the object is initially at rest, what is the velocity of the object after 10 seconds? How far did the object travel? And in what direction? So we have an initial velocity. 0. We have all these forces. The initial velocity being 0. We're going to apply a force for 10 seconds. We want to figure out what is the velocity of the object after 10 seconds. Well, for us to be able to find our velocity, we need to be able to find acceleration, because we have v final is equal to v initial plus at. Displacement is v initial t plus 1/2 at squared. V final squared equals v initial squared plus 2ad. Well, I know my time is 10 seconds. Time is 10 seconds. We know initial velocity, 0. But I want to find my final velocity, which means I need to calculate acceleration. Well, the only way we have a calculating acceleration, we have force equals mass times acceleration. So we have acceleration as force divided by mass. We have a 2 kilogram mass. So what we need to determine is, what is our net force here? What is our net force? Well, if we take a look, we're pulling sideways 1 by 2 newtons, 1 by 6 newtons, and we're pulling to the right 8 newtons. We want to find the sum of the forces. So we need to add all these forces together. Well, we have one going vertically upwards, one going vertically downwards, or if I'm looking at it on top, I'm going left and right, whatever. What do we have as a net force in the vertical world?
4 up.
Yeah, we're going 4 newtons upwards. Because if this was 2 and 2, we have a tug of war that's a tie. But since this is pulling 6 newtons, this is 2 newtons here, we have a net force of going 4 newtons upwards. But we have nothing to counterbalance the horizontal, so once again we have to take the sum of these vectors. Victor? We need to take the sum of these vectors. We need to add them together. Well, how do I add vectors together? Tail to tip, tail to tip, tail to tip. So I got 4 newtons going up and 8 newtons going this way. So we got 4 figs going up, we got 8 figs going to the right. I want to take the sum, which means I need to find the resultant vector. Victor? So we have to find our force resultant. Well, this one's sort of nice because I'm just going up and down, left and right. If I'm going up and down, left and right, I got my good old buddy Pythagoras. Where'd you go? We got our good old buddy Pythagoras. That will allow me to find my resultant force. Because we have a right triangle here. Lucas, what do you come down to?
8.94.
8.94. We have 4 squared. Fr is equal to 4 squared plus 8 squared. So we have 16 plus 64, or 80. That's force resultant squared. So we have F is equal to square root of 80. And what did you say it was?
8.94.
8.594 figs. So that is our resultant force. If that is our resultant force, the sum of the forces, or my force net, is 8.94 figs. This is equal to the mass times acceleration, which is 2 times a. So the acceleration of this object. Yes.
Give us any answer to
That's fine.
that. 4.5 meters per second squared.
4.5 meters. Or if I go out what I did there, 4.47 meters per second squared. So that's our acceleration of the object. Once we find the acceleration of the object, we have V final is equal to V initial plus AT. V final will equal 0 plus A, which we just found to be 4.47 meters, times our time, which is 4.47 meters per second squared, times 10 seconds. So the velocity after pushing this for 10 seconds is 44.7 meters per second. How far did the object travel? Well, we have displacement equals V initial t plus 1/2 AT squared. Or we could use the other one, but then I'd have to really solve for D. I don't want to solve for D with that. So I'm going to utilize this. 0t plus 1/2 A 4.47 times 10 squared. Brandon, what did you come up with? 224 meters. Now we probably should get a direction in here. A lot of times the direction comes off the horizontal, so I probably could have drawn this a little differently. So if this is my alpha here, this is 8 and this is 4. We can find this alpha from the horizontal. My tangent of alpha would be 4/8. Or 1/2. We can take the inverse tangent, find the angle. Nate, what do you get for an angle alpha?
26.57 degrees.
So we have my acceleration is, and all this is going to be the same, 26.57 degrees from horizontal, which I can come over here at 26.57 degrees from horizontal, which I can also take to my displacement, 27.57 degrees from horizontal. It tells us the direction that we're going to be going in. So with all these forces acting on this, we're going to be going in this direction from the horizontal. The object will move. The object will move this way. Because it's 26 degrees or 27 degrees from the horizontal. So it's going to be moving upwards. And that's if we're on a frictionless table. An object has a mass of 10 kilograms. What is the force of gravity on the object? What is your force of gravity on the object? Well, force is equal to mass times acceleration. What is the acceleration in the vertical direction? Yeah, 9.81. Negative 9.81. So this is just gravity, which is our acceleration, negative 9.81 meters per second squared. Ouch. So we have 10 kilograms. Times negative 9.81, so we have a force of negative 98.1 figs. This is our book dropping. Once again, this is a field force. An inclined plane, a hill. It is a slanted surface. A slanted surface, an inclined plane. If we have an object on this inclined plane, and I start to raise to a different height, the object will fall, magically fall. I didn't touch it, there was no contact force there, it is just pure magic, wizardry that is going on as I take it to there. No hands. Never touched it. Well, the question is, why did it slide down the hill? Why, when I put it here, or why, if I give a little shove in the wintertime and I'm on a sled or skis, I slide down the hill. You're a skier, aren't you? I could go up there and ski the slopes. Or you snowboard. You're a snowboarder. Who else is snowboarders here? You're the only one that goes on the snowboard trips? Why do you go down the hill?
Gravity and friction.
Yeah, it's a little slickery, okay? You got snow there that's packed down, it's slick, which is very close to what we're creating, a very frictionless world. Because if you're snowboarding correctly, you just don't go to the store and get the snowboard and then go up to the hills and start going down the hill.
Shred an arm.
Huh?
Shred an arm.
What do you do to the bottom of the surface of your board?
You wax it.
Yeah, wax it down. What are you trying to do?
Go faster.
Yeah, you're trying to reduce the surface friction. Trying to go faster. Because faster is better. Yeah. I've been snow skiing once. There's a reason why I've only been going snow skiing once. My friends, oh gosh. 30 years ago. You need to go skiing, maybe 35, you need to go skiing with us. They're skiers. I went, I've never done this before. So it's okay, you'll be fine. They put me on the bunny hill. Okay, here I am, a grown man on a bunny hill with all these little kids going down the hill. It took me about 10 tries. I finally made it down the bunny hill without falling down. When they saw me do that, said, okay, you're over there on the big hill. I went, okay, I have this figured out. I got this. I'm George Lopez. Okay, I got this. I got it figured out. And first off, I'm not too much of a fan of the ski lift because of the fear of falling. I'm not afraid of heights, but I'm just afraid of falling. There's a difference. Get up to the top, get off the ski lift. Of course, I tumble off of that and roll down the little hill there. It's like, okay, I'll let everybody go first, and I'll start going. Nice and wide, really wide, working myself down the hill. Okay, doing good. I'm going nice and slow. I'm making it down. This is good. This is good. Until you get to a certain point where it goes from this to that. No longer can you go side to side anymore. You can try, but it's not good. So all of a sudden, there you go. Not good. Not good. After a certain point, I mean, I was going so fast, at least I felt like I was going about 90 miles an hour. I just bailed. I went down, boom. Went down, people up in the ski lifts give me 10s for my dive. Okay, snow going everywhere. The problem was, I lost the ski. So there I am, halfway down the hill on one ski. It was completely miserable. It was miserable. Finally, I was able to get myself to the bottom of the hill, got my ski, got back on the lift, made it, didn't lose my skis the next 2 times. I thought, okay, I'll go again. Well, get on the ski lift, my toe on my ski catches, snaps off. So I get to the top of the hill with one ski to get off the ski lift. It was very humbling. Very humbling. I finally made it down the last time. I said, okay, I'm out. Drop the mic. I'll go inside where it's warm. I don't like cold anyways. But you ski people, I give you a lot of credit because I can't do that kind of stuff. That one time was enough for me. The next day I get up, and the next couple of days I'm bruised. You're bruised all over the place from it. I found no joy in that. It's just like roller coasters. I find no joy in scaring the bejesus out of myself on a roller coaster. I know. I'm sorry. If I want to do that, I don't need that. I don't need to feel like I'm going to die.
Did anybody say yard sale when you fell?
No, I don't remember. That was a long time ago. I just remember people on the ski lifts they're going up and hey, 10, nice job, nice fall.
They usually, when a skier crashes, you usually say yard sale because all their stuff's all over the place.
Well, when my ski, as I'm laying there and watching my ski go all the way down the hill, I'm thinking this is not good. At least I knew it was not good. I didn't know how to solve the problem. You try to go one ski on and one ski, you just keep tumbling at that point. You should try it sometimes. It's fun.
I did it once. For a weekend.
Yeah? Have you ever done it again?
We're taking a trip.
I would if I got the chance.
Yeah.
I thought it was, once you get through the stage of, like, once you kind of pick it up a little bit, it helped going for a couple days at a time.
It's fun.
Yeah. Give me a tube. I'll go down on the tube. That's fine. I'll go fast on the tube. I'm really close to the ground. I don't lose a tube. And if I do lose a tube, that's fine. I'm not going to lose that because I'm sitting on it. Anyways, any slanted surface is an inclined plane. What's going to happen on this inclined plane? What makes an inclined plane? What makes it slide down? Well, gravity. Gravity makes things slide down a hill. How many times we've been in nice clothes, nice fresh pair of jeans, and we start going down a slippery slope, and all of a sudden we slip. And boom, we go down on one knee, and your knee gets all muddy, or your pants get all muddy. Okay, you're trying to baby step down the hill. Baby step, you know it's slickery. You know, you're trying to baby step down there, all of a sudden, boom, there you go. We've all been there. At least I have, didn't I? Yeah, I know a lot of you guys are perfect, but you don't fall. Never. Okay, gravity. Gravity makes you slide down this hill. When you go sled riding, when you go inner tubing, a tube on sled riding, you go out there to Jericho Hill, is that where it is? I don't know, there's places to go out south of here that people used to always go sled riding at.
Christmas Run in Worcester is nice.
Hmm?
The only place I really ever gone to go sled is Christmas Run in Worcester.
Yeah, is it pretty big? You know, the old school, we used to go down to the middle school and elementary school, the hill at the middle school and elementary school, that was the hot spot to go to. When my kids were little, I spent a lot of hours down there with my kids, down there in the sled riding slopes.
The hill above my Uncle Mike's,
Yeah.
it's huge. It's fast.
The problem is, you go all the way down that huge hill,
We got,
you gotta find a way to get back
we
up.
got the gator, we just hop on the gator and drive back up.
There you go. You have one person doing that, right? Just doing the trip. Well, gravity, though, acts downwards. So gravity acts in this direction. This is your force of gravity, which is the weight of the object, what we just calculated up above or in the front side. Your force of gravity goes downwards. The problem is, though, as we talked about, our motion is in this direction. This is your motion down the hill. This is your motion down the hill. Which means if that's our motion going down the hill, this is going to give you velocity. And to give you velocity, we have to have acceleration. It's all moving down the hill. This force acts downwards. It's not in the direction of our motion. And remember back to what we did on the front side here. our force, our net force is going in this direction, our motion's going in this direction, our velocity is going in this direction, our acceleration is going in this direction. Our net force is here. The only thing that we have in this case, the only force that is magically making us go down the hill is this force of gravity, the weight, which is not in the direction of our motion. So we have a problem there, because we're talking about motion this way, the force is going this way. Well, the force should be pulling it downwards, straight down. Why? Because the force is going to give you a direction for motion. And we don't have that here. So what we have to do is we have to talk about two different components. We have a force parallel and a force perpendicular. The force parallel is a force component of gravity on an object that will cause the object to slide down the plane. It's a force component of gravity on an object that will cause the object to slide down the plane. This gives us that force right there, which is going to be the force in the direction of the motion. If that's the force in the direction of the motion, it will give me acceleration, and I can deal with the velocity then. Okay, it gives me that force in the direction of the motion. It gives us the force in the direction of the motion. And think back to when you just had this 10 kilogram mass. Okay, we have this 10 kilogram mass here. It's pulling it downwards. I have a book. Oh my. If the popo don't come, I might get shot. Okay, it's going downwards. Okay, that is our weight that I forgot to do over here. That's the force of gravity on the object. The force of gravity is going to pull us downward. The motion of the body of this book is going downwards. Okay? It is boom, going down. That's my force of gravity. That's the weight of the object. Over here, we have the weight of this object. It wants to go downwards. Problem is we got a slant there. We have an inclined plane. So our force in the direction of motion is called a force parallel. We have the force perpendicular. The force perpendicular, it's the force component of gravity on an object that will maintain contact with the plane. It will maintain the contact with the plane. It pushes it down on the plane. This is also called a normal force. And we just learned in calc class we have tangent lines, and then we had normal lines, which are perpendicular to your tangent lines. This will be perpendicular perpendicular to the surface of the plane. It's what keeps the object pushed down on the plane. So if we look at this component, this will be perpendicular to the surface, but also perpendicular up here. You have parallel and perpendicular. So this here is your force perpendicular or your force normal. We will stop here today, and we'll get into some problems tomorrow. Got too much into storytelling time.